Okay, hello and welcome. This is SFU Math 232. My name is Brenda Davison. We're going to discuss today section 7.4, the dimension theorem and its implications. Okay, so let's figure out what this theorem is. What we're going to do is start off with an example here. We're going to find the rank and nullity of this of the matrix. Well, we're going to do it of the matrix A. Where A is a 4 by 5 matrix and U, here this matrix, is its reduced row echelon form. Okay, so we can see that this matrix U is in a reduced row echelon form, and there is some matrix A that reduced to this. Okay, so I'm just going to make a bunch of statements about this matrix. First of all, it's 4 by 5, just like A is. So it has 5 columns. So U has 5 columns. It has, let's think, 2 leading variables. It has 3 free variables. We have the situation that A is row equivalent to U. And so what do we know about the rank of A? The rank of A is the dimension of the row space of A. We also know that the row space is unchanged by elementary row operations. So that means that the rank of A is equal to the rank of U. And we can see what the rank of U is. That is the number of non-zero rows. So the rank of U is also the dimension of the row space of U, and we can see that that is 2. Okay. And then the nullity of A is the dimension of the null space of A. Okay, elementary row operations also do not change the null space. U has 3 free variables. And we have then that vectors that satisfy, I could do a better job with that, that satisfy ux equals to 0, that is, that are in the null space. The vectors that comprise the null space of U will look like this. X equals R times some vector plus R, say another scalar, S times some vector plus a third times a vector. Because of the 3 variable situation, we have 3 degrees of freedom. Okay, so that means that the null space has dimension of 3. This is dimension 3. So the null space of A has dimension 3. So the nullity of A is equal to 3. So we have the rank of A is 2, and that the nullity of A is 3. Just sort of box the main thing. So we have the rank of A being 2, and the nullity of A being 3. And we will notice, and this is going to be backed up by a theorem in about 2 seconds, we will notice that the rank of A plus the nullity of A is equal to 2 plus 3. That is equal to 5. And that 5 happens to be equal to n, this number right here, the number of columns. That's equal to n, the number of columns of A. just sort of reminding ourselves what all these terms mean, and then observing this relationship here. And then we're just going to state that on the next page here. In this theorem, we have a bunch of things here. So we have a homogeneous linear system with n unknowns. That's the number of columns. And the reduced row echelon form has r non-zero rows. That means there are r leading variables and n minus r free variables. Okay, so then there's a bunch of statements here. The number of leading variables plus the number of free variables has to be equal to the number of columns. We saw this right at the beginning. This is not new. We had this when we first started to look at the fact that we could represent systems of linear equations in matrices. Okay, so let's see how else we can say this. The number of non-zero rows of U plus the number of parameters in the general solution of AX equals 0 is equal to n. Okay, non-zero rows plus the number of parameters in the general solution. Okay, the size of the basis for row A is equal to the, the size of the basis. So that is the number of vectors in the basis for the row space of A, which is going to be the same number of vectors in the basis for the row space of U, plus the size of the basis for the null space of A is also n. And we can say that here, the dimension of the row space of A plus the dimension of the null space of A is n. Okay, and then we can just continue on. This is what our next thing is going to say. That is that the rank of A plus the nullity of A is equal to n. Okay, so that is the dimension theorem for matrices. If A is a m by n matrix, the dimension of the row space plus the dimension of the null space is n. Okay, that sometimes is also called the rank nullity theorem, for obvious reasons. Okay, so in our textbook here, they call it the dimension theorem for matrices. Okay, so what are some consequences of this? Well, if we have a matrix of rank k, then the nullity is n minus k. Every reduced echelon form of A has k non-zero rows and m minus k 0 rows. The homogeneous system has k leading variables, and n minus k free variables. Okay, so this is just a bunch of ways of sort of saying the dimension theorem, really. So we can use these things to figure stuff out. Okay, let us just take a look at an example of what we could say about a matrix. We imagine we have a 4 by 7 matrix. So we have some matrix A. It is 4 by 7. That means it has 4 rows, 2, 3, 4 rows, and it's got 7 columns. 1, 2, 3, 4, 5, 6, 7. So those are, we've got, I guess what we have, the way that I've done this, 1, 2, 3, 4, 5, 6, 7. Well, we've basically got numbers sitting at these locations, at all these things. That's where the numbers are. Okay, we've got 4 rows and 7 columns, like that. And the numbers are those x's, whatever they are. So we have m is 4 and n is 7. This is the rows and this is the columns. Okay, now we're asking, can A have a two-dimensional null space? So let us say then, if the nullity of A is equal to 2, then by the dimension theorem, then the rank of A is going to have to be 5, right? Because the rank plus the nullity is equal to 7. Because rank A plus nullity A is equal to 7. 2 plus 5 is 7. Okay, so however, let us think. The rank A is determined by the number of the number of non-zero rows in the reduced echelon form of A. Now we've got it in matrix A, and it's got 4 rows. So there's no way it can have 5 non-zero rows. So there's 4 rows in A. A has 4 rows. Rank A is at maximum 4. So it can't have a rank of 5, so it can't have a nullity of 2. Therefore, rank A not equal to 5. That implies that the nullity of A cannot be equal to 2. Okay, what if you tried the same thing with a 4-dimensional null space? Okay, that would imply, by the same theorem, by the dimension theorem, that rank of A is 3. And for example, the reduced row echelon form of A could look something like this: 1, and then there'll be some other numbers. Let's just do it like that. There's 7 of these numbers going across here: 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6. 2, 3, 4, 5. Maybe got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay, 7. And then we had 4 rows. It could look like this. At this point, what I've drawn here would be a matrix with a rank 3. So then if that was the case, it had rank 3, it looked like this in its reduced row echelon form, then the nullity would be 4. And indeed, so we can have this matrix A could potentially have a 4-dimensional null space. Whether it does or not, of course, depends on what the numbers in it actually are. Okay. If AX equals 0 has only the trivial solution, what does that mean? That means the vectors that are in the null space of A, this would mean the null of A would be precisely equal to the 0 vector. So that then that means the dimension of the 0 vector is 0. So that means that the rank is n. And sometimes you will see, in this case, particularly when the matrix is square, somebody will say it's a full rank matrix. The rank of A is the maximum that it can be, n. Has no non-zero rows in its reduced row echelon form. Okay, are you ready for the big, the big moment? Our unifying theory grows, and it grows, and it grows. And here it is now. Okay, look at that. Now it's up to R. So what's being added here? These two guys here. It's basically saying that when we have all these conditions that we've been talking about, that would imply a full rank matrix. Or now notice, of course, our theorem here is on the square matrix. That it's a full rank matrix, and the dimension of the null space is 0. So again, now any one of these statements implies all of the other ones. So just to say that again, this is an important point. If, for example, I could say I have a vector A and its row vectors are linearly independent. And I've ticked that that's true. That means that all these other statements are also true. You can immediately claim any of these other statements based upon one of them being true. Okay. Let's see what we can perhaps use some of this stuff for. Imagine that we have some number of vectors that are linearly independent, a set of vectors, and but we yet don't have a basis for Rn, and we want to extend that set and manufacture a basis for Rn. That's actually sometimes, well, not super easy to do. So you'll notice, for example, sort of here, if you flip in the textbook to that proof there, what does it say? It says something like this: there is some vector v1 in V that is not a linear combination of the vectors in S. Okay, fine. It doesn't tell you how to find that vector, and then it just says add this vector to the set. So you can imagine if I'm, say, for example, in R5, and I say to you, here's 4 linearly independent vectors. Find a 5th vector to make this into a basis for R5. How do you select that 5th vector so that you're ensured that it is linearly independent? So that's what we're going to talk about here. We've got some number of vectors, in this case k of them, and we're in Rn, and here we're basically thinking in this problem that k is less than n. Because if k is equal to n and they're linearly independent, we already have a basis. If k is bigger than n, then we know that we have some dependent vectors, and we should just find out which ones those are and toss them out. Okay, so what should we do in order to extend our set, which does not have enough vectors into it, up into the place where it is a basis for Rn? So this is going to be our procedure. Form a matrix having the vectors as rows, because then the row space will be the span of those vectors. And then we will find a basis for the null space of A. We know how many vectors that will have. It'll have that many there, n minus k. And then since the null space of A is the row space of the orthogonal complement, when we find the basis vectors for the null space, they are orthogonal to all of the vectors we started with. And so then they are not going to be linearly dependent upon them. So those are the ones we can add in order to form the basis to get enough vectors and have them all linearly independent so that we have formed a basis for Rn. Best thing to do is see this amazing procedure in action. Okay, so here we are. Here's the kind of problem. We've got two. We've got 2 vectors here. They are in R5. There's 5 components. And we want to extend this set. We want those 2 vectors to be in the set, and then we want another 3 vectors in the set, and that's going to form a basis for R5. So it's going to have to span R5, and it's going to have all of them linearly independent. So here's how we're going to do that. We're going to form the matrix A, and into the matrix A, we are going to put 1, 4 as rows. 2, minus 7, 0, the 2 vectors we've been given. There they are. Okay, and then we are going to, forget it, I'll write it again. We are going to then find the null space. So we want to find the values of x, all of the vectors x that make this statement true, ax equals 0. So to do that, we take this here like that. We augment it with 0, 0, and then we would perform the Gaussian elimination, and we would maneuver until we get to reduced echelon form. Mercifully, this guy is already in reduced echelon form, so we don't have to do any Gaussian elimination steps. We have our 2 leading variables right there. So then we can identify what the vectors x look like that are in the null space. So we can see from this, let me just maybe up here, this is x1, x2, x3, x4, and x5. So we see that x2, x4, and x5 are free variables. So I'm going to just assign them to some parameter like that. And x2 I'm going to assign to r. Okay, then I'm going to see what x3 and x1 look like. Well, x3 is going to be 3s minus 5t. That's coming from this row right here. And then x1 will be minus 4r minus 2x3 plus 7x4, like that. And then x5 is not there, 0. Okay, so I can simplify that. Minus 4r plus s plus 10t. Okay, so now I can write out the solution set here for the ax equals 0. It looks like this. All linear combinations of these guys here. R times that plus s times this plus t times this. Okay, these vectors here, these three vectors, these guys, those form the basis. Those are a basis for the null space. Well, these are basis vectors for the null space. Not sure why things are jumping around a little bit. Yeah, just basis vectors for the null space. Okay, so those vectors are orthogonal to v1 and v2. And so they are linearly independent of v1 and v2. So let me just write that down. It's an important point. These vectors right here are orthogonal to v1 and v2, which means they are linearly independent. Of v1 and v2. Okay, so that means that I can add them to v1 and v2. These three vectors, I can add them to v1 and v2. I will have 5 linearly independent vectors in R5. That will be a basis for R5. Okay, so let me do that. So then let me say here, then this is my basis for R5. The two vectors I was given, that one, and I was given this one. Now I'm going to add these three vectors that I found. Like that. And this set here, set of vectors, is a basis for R5. It's basis for R5. What else do I want to say about this? Let me just show you via an example. You should check them all yourself. First of all, it'll identify if I've made a mistake, and also you maybe gain some insight about what's going on. So, for example, here's one of my new vectors, that guy there. Let's just take that and take the dot product here. 1, 4, 2, minus 7, 0, dot, minus 4, 1, 0, 0, 0. Okay, so I take the dot product and I get 0, right? Minus 4 times 1 plus 4 times 1. That has to happen. I mean, that is what is supposed to have happened. We attempted to find the basis vectors for the null space. So each one of these guys here has to be orthogonal to these two guys here. Okay, you could check that. Make sure that's the case. Okay. Let's keep going. So this is a major theorem. the dimension theorem. And we're going to see it just in a slightly different guise here. This is not that exciting in some sense. It's just a statement. We said it for a matrix. We said if we have a matrix A, then the rank of A plus the nullity of A equals the number of columns in A. That was our dimension theorem for matrices. Now we're just going to state exactly the same thing, just in a marginally different way. And we're saying if W is a subspace of Rn, then the dimension of W plus the dimension of the orthogonal complement of W is equal to n. Okay, so let us just say a few things about this. One is when we had a matrix, we could form a matrix here with the basis vectors for W. Okay, and then we would have that the rank of A would be equal to the, well, this is always true anyhow, the row space of A. Okay, so take a basis for W. Put these as rows of A. Then we have that the dimension of W, the number of basis vectors for W, is the same as the dimension of the row space of A, which is rank A. Okay, W is a subspace of Rn. Let's write that down. W is a subspace, subspace of Rn. That means that A has n columns. The vectors have n components. So the null space of A is the orthogonal complement of W. So then we end up here. The dimension of the null space of A is equal to, well, we call it the nullity of A, and that is equal to the dimension of the orthogonal complement of W. So then we end up with the theorem is saying, the dimension of W plus the dimension of the orthogonal complement of W is n. We basically showed that the dimension of W, our claim is just to do one from the other. So we have here the dimension of W is equal to the rank. So here's the rank. And then the dimension of the orthogonal complement of W is the nullity, and that's right here. And so this is the dimension theorem for matrices, if you look at it that way. Okay, same thing. Okay, what else can we say here? Let's take a look at this. If we have a subspace of Rn with dimension n minus 1, we have been calling that, and we will continue to call it, the hyperplane through the origin. The dimension of the hyperplane through the origin is 1 minus the dimension of the space. So here we've got W. The dimension of W is n minus 1. Then we're claiming here that there's a non-zero vector n such that W is the orthogonal complement of n. Let me just suggest an exercise for you. Draw the 2D and 3D case of this. Okay, identify W, draw a picture of it, identify what n looks like. Okay, we did this actually in a previous lecture, so it'd sort of be, I think it was just the last lecture, in chapter 7. Anyways, I can't remember if it's 7.2 or 7.3, but we have done this, so maybe get that back into your head by drawing a picture. Okay, so we have here that the dimension of W is n minus 1, and so that means that the dimension of the orthogonal complement of W is 1. That's by the dimension theorem for subspaces. okay, because n minus 1 plus 1 is equal to n. Okay, so now we're looking for a vector. We know it's a vector because it has dimension. Well, actually, let me backtrack on that. I don't want to jump ahead of myself. Okay, leaving it at that. So first, I just want to not confuse you. That I'm gonna write this guy here like this, the orthogonal complement of the vector n. Don't confuse that with this n here. This n is that n there, Rn. Okay, we've got a vector n and we've got a number n. The vector n should and will hopefully always have the little thing over top so we can recognize it. And in the type notes there, it's bold-faced. Okay, so we have these two things here. Now, the orthogonal complement of W is the span of n. And W is equal to the orthogonal complement of W, and we take the orthogonal complement again. That is the span of n, like that, and we take the orthogonal complement, and then we see that that is the orthogonal complement of n. So W is a hyperplane through the origin with normal n. Okay, a few more things here. I've got really just another couple of examples, and then a wrap-up theorem at the end here. So now, suppose I've got a hyperplane in R4, and it's got, so this has to be the case. The dimension is 3, and we want to find the normal of this hyperplane. So we want to find the vector n in R4 such that W is the orthogonal complement of that. Okay, so what we write here is W is equal to the span of the vectors we're given. This is what it says. It's a hyperplane with this basis, so it's equal to the span. Like that. And we know, because it's a basis, these vectors are linearly independent. Okay. So we have that then, because there's 3 vectors there, the dimension, and they're linearly independent. The dimension of W is 3. I mean, that has to be that we got told it's a hyperplane in R4, so that has to be the case. So we were just going to note that, sort of a check on that, what we're doing. Note that 3 is equal to 4 minus 1. Okay, so W, I'm going to write W as the row space of A, where A is equal to the matrix that has these vectors as rows. Like that. Okay. The orthogonal complement of W is going to be n, where the orthogonal complement of W is the null space of A, which I can compute with my Gaussian elimination skills. So I'm going to go ahead and do that. So now I'm computing the null space of A. That is the solutions to AX equals 0. Okay, that's the null space of A. So I'm going to go ahead and do that. I take A. Here it is. 1, 0, 1, 1, 0, 1, 2, 2, 3, 0, 0, 6. I augment that with 0, 0, 0, and I go ahead with my Gaussian elimination until I get this into reduced echelon form. And so I'm going to do that. I will Copy this one out and this one too. And then I'll take row 3 will become, the new row 3 will be row 3 minus 3 times row 1. Like that. And then I'm just going to simply multiply row 3 by negative a third. So I'm going to get 1, 1, 0, 0, 1, 2, 2, 0, 0, 0, 1, minus 1, 0. Okay, so I'm now thinking, oh, hang on, something has gone wrong. Has it? 4, I got, oh, no, it has not. Okay, I'm fine. Okay, I think I'm fine. I don't have all the details in front of me here, so it's possible to lose something here. But let me just circle my leading variables, and I'm seeing that this x1, x2, x3, x4. So I can see that x4 is free. That's what I would expect. I'm looking for a single, something of dimension 1. So I would expect the one free variable, and I got that. So I feel at least that's a slight check on having not made a mistake. Okay. So let me write out, we've got x4 is equal to t, and then we end up with x3 is the same as x4, and then x2, that's from, this is coming from this row here, and then I'm looking at the next row up, and I'm seeing that x2 is minus 2 times x3 plus x4, and that's 2t, so this is minus 4t. And then x1, so this x2 is coming from this row, and then I'm looking at the first row of the matrix, and I'm seeing that x1 is minus x3 plus x4, and that is minus 2t. Okay, so then I can write out x1, x2, x3, x4 as 2 times, sorry, not t, that is a t, t times minus 2, minus 4, 1, 1. There it is. Okay, so that means that n is this vector here, minus 2, minus 4, 1, 1. That vector is orthogonal to v1, v2, and v3. So let us just write that down. You could confirm this yourself, but n dot v1 should be equal to n dot v2, should be equal to n dot v3, which should be equal to 0. So I'm just now looking back thinking, let's hope that's the case. Yeah, so I just mentally did this dot with that guy there, and I see minus 2 and then the plus 1 plus 1, and came to 0. Okay, so check, all of them should work. Okay. Final topic or thing we're just going to say here is there are some matrices that are of rank 1, and in fact we're going to see that we can get a matrix like this by evaluating an outer product. Now, up until now in the course, we did mention what this was way in the beginning, but for almost exclusively until now, we have been using the inner product, which we have mostly called the dot product. So we've always been using the inner product, dot product, and now we're going to come back to the outer product. So let me just as a contrast, a reminder, the inner product is a row times a column, and it looks like this. U transpose V, and it is equal to a scalar. Okay, what we are now doing is the outer product, and the outer product is equal to a column multiplied by a row, and the result of that is a matrix, not a number. Okay, let's just see an example here. So we're going to take the outer product, U B transpose, and that will look like this. Put it to more matrix notation. 1, 3, 2, minus 1. We're going to multiply that by 2, minus 5, and 7. And then the result of that is going to be a matrix that looks like this: 2, minus 5, 7, 6, minus 15, 21, 4, minus 10, 14, minus 2, 5, minus 7. So the outer product of those two vectors is a matrix. And you can see why this is always going to be this matrix that we formed here. Maybe I should just give it a name. Let's just call it A. That's original. The rank of this, so the rank of, I could say rank of A, or I guess I could write it like this: the rank of U V transpose is always going to be 1 when it comes up like this, because each row is a scalar multiple of, say, the first row. I could just like take a look at that first row, and I can see that all of the other rows, by the way this thing was formed, I mean, I took 1 times this, and then I took 3 times this, then I took 2 times this. So they're clearly going to be scalar multiples of each other. So if I were to do, you can do it if you want, I could do the Gaussian elimination on this guy, and I would get down to, I would get 3 0 rows, and I would get the first row. And then I would say, oh, look, it has the rank of A is 1. Okay, so that always happens. So what this alerts us to is, should we get a matrix and observe that the matrix is of rank 1, then we can factor it into the product, the outer product of two vectors. So I'm just going to make a note of that. So you can factor a rank 1 matrix into two vectors whose outer product is equal to the matrix. Okay, that's what our final theorem here is going to tell us. If U is a non-zero column vector and V is a non-zero column vector, then the outer product is a rank 1 matrix. And conversely, if matrix A is rank 1, then A can be factored as U times V transpose for some column vectors U and V. Okay, so I'm just going to backwards the example that we had before. Let us take here A. We just saw this matrix in the last example. Let's just take this matrix. Here it is. There, the matrix. And I'm going to just simply, well, here's what I'm going to do. Notice it is, let me put it this way. Notice the rank of A is equal to 1. If you don't just notice that, well, you can row reduce, and you'll get down and you'll get 3 0 rows, and you're like, oh, I see, it's a rank 0 matrix. Okay, then what I can do is take V transpose to be any non-zero row. Okay, so I mean, when we formed this thing, that was what V transpose was. But I'm going to just, in essence, to show that this, it doesn't matter which one you do, I'm going to pick the next option. Okay, I'm going to pick this guy here. So I'm choosing any non-zero row, and I'm making that V transpose. Okay, that means V transpose is equal to 6 minus 15 and 21. Okay, then what I want to do is I then form U as the scalars needed to produce all the rows. Okay, what do I mean by that? Let's just write it out. So in this case, it means that U would be equal to, and the first entry in U is 1/3. Why? Because 1/3, okay, I'm just write it over here. 1/3 times 6 minus 15 and 21 is equal to 2 minus 5, 7. I don't really need to commas here. Like that. 2 minus 5, 7. And that is that first row right there. Okay, so the next entry is going to be 1 because 1 times V transpose gives me the second row. The next entry here is going to be 2/3 and then minus 1/3. Okay, there we have it. So now I have factored A into, so I'm saying here that A is equal to U V transpose. There we go. And of course we can do this multiplication now and just, this is a little bit messy. We can do this multiplication and we will see that we get matrix A back. So I do 1/3 times 6, I get 2, 1/3 times minus 15, I get minus 5, etc. So you can complete this multiplication. You'll see you'll get back here to the original matrix. That is the rank 1. The rank 1 matrix. You'll notice that this factorization here is actually not, it's two different vectors than the ones I started with to form A in the first place, because you can use any non-zero row. All right, that is it for section 7.4, the dimension theorem. I will be back with our next theorem in the next lecture, 7.5. Thanks a lot. Bye.